So I've got a good question here. So as we found the variance of home prices in a neighborhood, what units is the variance going to be in? Right, so let's assume this neighborhood's in the US, so we're dealing with dollars at least. All right, well, let's look at that formula again for the variance. All right, so I'm going to add up the distances to the mean squared and then divide by n minus 1. All right. So if I've got home prices in dollars, what's the mean home price going to be? Still in dollars. So this is going to be in dollars minus dollars, right? So $7 minus $5 leaves me $2. Okay, so I'm still in dollars. That's good. Then I square it and then divide by n minus 1, which has no units. So I'm actually going to be, my units of variance are going to be dollars squared, which I swear an economist told me that he could understand completely what dollars squared means. I don't believe him to this day. That makes no sense to me. I don't know what squared dollars are. Dollars make sense, but squared dollars means nothing to me. So that's a problem that we need to fix, which is how we get to the standard deviation. When I've got something squared and I want to get back to my original number, what do I do with it? We did this in our very first practice activity for the course. I wanted to make sure that you knew why we call something a square root. It gets us back to the root of squaring something. So if I have something in dollars squared, all I got to do is take the square root of it, and I'll get back to my original units that I had. So that's the whole point, honestly, of the standard deviation. We've got a whole different word for it, and it'll have some cool properties that we'll talk about later, and I'll explain why it's called standard and why it's called deviation in a little bit. But for now, what we really need to know is that this thing itself, s squared, is the sample variance, and s is the square root of s squared, right? So first off, let's be careful about negative numbers, right? This equation is not true necessarily actually it's just not true if s is negative, right? If this was like -1, -1 squared becomes 1, square root of 1 is 1, which is not -1. So this is not true if s can be negative. But can this thing be negative ever? Let's be careful with that, right? Because I also don't want to take square roots of negative numbers. That gets us to this imaginary stuff. I don't want to do that. So, well, this thing could be positive or negative, but once I square it, a squared number is always going to be at least 0, right? It can't be negative. A negative number turns positive, and a positive stays positive. So this is going to be positive. And then when I add up positive numbers, it's positive. And my sample size better be a positive number. So if I've got a positive number divided by a positive number, it's going to be positive. So good. I don't have to worry about that. So even though this may not be true in math class, it's certainly true in our situation at least, because s squared is always positive. So this thing, this s, is the standard deviation. I am never, ever going to ask you to calculate these by hand. But I'm unaware of any software that gives you both. They give you one or the other. And so we need to be able to go from one to the other. So in other words, I don't want us to go from our raw data to one of these, but if we're given a sample variance, I want us to know how to get a standard deviation. And realistically, what does that mean? If I take the square root of my sample variance, I'll get my standard deviation. Now what about the other way? If I've got my standard deviation, how do I get the variance? I just square it. Okay, so this is just either taking a square root or squaring something, which is, again, part of why we required some kind of scientific calculator or scientific calculator app for this course, just to be able to do simple calculations like that, not this big mess here. Okay, so that's what I want us to get out of standard deviations and variances, how they relate to each other, and why we're going to prefer the standard deviation in general is because it's going to get us back in our original units. Now let's quickly talk about a couple of things. Can this be negative? Either one of these? Okay, well, no. We already talked about how this can't be negative, which means the square root of positive is still positive. So at least when we do it like this, so yeah, we're good. We're good, right? So we're taking the positive square root. So the standard deviation can't be negative. Can it be 0? Remember, these were the average square distances to the mean. What if all my values were the same number? Say I just walked in on a freshman PE class, everyone in there was 19 or something. Well, now the average is going to be 19 for the age, and then each person is 19, so 19 minus 19 is going to be 0 for every one of these. And adding up a bunch of zeros gets me 0. And I don't care what my sample size is, 0 divided by any number is 0. So, yeah. Actually, I can get 0. 0 is the smallest I can get, right? Because it can't be negative. And remember, these were the typical distance. So now that I have a standard deviation, I can roughly talk about, instead of average square distances to the mean, kind of roughly average distance to the mean. That's not really how it works out, but let's just pretend like it does. So we're just saying average distance to the mean. Roughly. Bigger distances mean more spread, right? So bigger standard deviations mean more spread in the data, right? That's what we need to get out of this. Interpreting the standard deviation directly, as far as a standard deviation of 7 units, what exactly that means is just not going to be clear. But I can give us some rough understanding of how to interpret this thing. So let me talk about these properties of standard deviation real quick. Okay, it's never negative. Could be 0. We're in the same units as our original data, which is why we're going to prefer the standard deviation over the variance. Larger standard deviations imply a greater spread, and then just a rough interpretation. Most of the data is within 2 standard deviations of the mean. Almost all of the data is within 3 standard deviations of the mean. All right, so let me just explain what I wrote there. Let's say for student ages, we've got a mean of 22.5. Oh, let me take out decimal places. I don't want to complicate this. And I've got a standard deviation of 2. Okay? That means in my data, the great majority of the data is going to be within 2 standard deviations. Almost all of it's going to be within 3. So what do I mean when I say that? Well, let me take this 22 and subtract off 2 standard deviations. So 2 times 2 was my standard deviation. That gets me 22 minus 4 is 18. And then 22 plus that same 2 standard deviations gets me 26. So I'm making the claim that the majority of the observations were between 18 and 26. And if I change that to be within 3 standard deviations, so I'm looking at 3 standard deviations worth of difference here. 22 minus 6 gets me 16. 22 plus 6 gets me 28. I could say almost all of the data was between 16 and 28. So that's about all I can get directly out of a standard deviation in terms of interpretation. What we'll often use it for is to get at something else or to compare one standard deviation to another with the same type of data at least. Right. So if I knew the standard deviation for student ages at Casper College is higher than it is at University of Wyoming, that means there's more spread in ages. There's more variability in ages of students at Casper College than there is at UW. So not going to be our easiest to interpret, horrible to calculate, but it's going to have a great advantage in that it's reliable. I'll talk about that in our last section on these measures of spread, which will be choosing the best one.